Okay, good evening everyone. So we are given a task which we are supposed to find a solution for this question number 4. Consider the base plate of an 800 volt household iron with the thickness of L equals 0.6 centimeter. Base area A equals 160 centimeter square, and given the thermal conductivity of K is 60 volt per meter dot Kelvin. The inner surface of the base plate is subjected to uniform heat flux generated by the resistance heater inside. When the steady operating conditions are reached, the outer surface temperature of the plate is measured to be 112 degrees Celsius. Disregarding any heat loss through the upper part of the iron. A. Express the differential equation and the boundary condition for steady one-dimensional heat conduction to the plate. B. Obtain the relationship for the variation of temperature in the base plate by solving the differential equation. And C. Evaluate the inner surface temperature. So before we start doing this question, so we have to list down all these categories, which are the assumptions, properties, analyze, and move on with our solution. So our assumption for this question is, number 1, heat conduction is steady and one-dimensional. Second, thermal conductivity is constant. Third, there is no heat generation in the plate. And fourth will be the heat loss to the upper part of the iron is negligible.
Okay, next the properties is given, which is the thermal conductivity is 60 watt per meter degree C. And the last part is the analysis, which is the upper part of the iron is well insulated, and thus the entire heat generated in the resistant wires is transferred to the base plate. Then we can find the heat flux by using formula heat transfer over area. Heat transfer was given, which is 800 watt, and the area also was given, which is 160 cm squared. So we get the heat flux, which is 50,000 watt per meter squared. Then we can use differential equation on page 83, which is d squared t over dx squared is equals to 0. And then we can use the specified heat flux formula, which is Q, which is heat flux is equals to negative K dt over dx, which is we already get here 50,000 watt per meter squared. And the outer surface temperature was given, which is 112 degrees C.
So, moving on to question 4 part B. The question asks, obtain a relation for the variation of temperature in a base plate by solving the differential equation. So the question asks us to obtain or create a relation by solving differential equation based on temperature. So if we look at the diagram, this diagram illustrates the question. So the base plate, first the inner surface, which is on the left side, the boundary condition is heat flux Q, which we already found in part A, Q, and the second boundary condition at this part is x equals to 0. X is the thickness. We start with x equals to 0. Okay. For the outer surface, which is the right side, the boundary condition given is T2, which is 112 degrees Celsius. And the x is L. X is the thickness again. X is the thickness, so x is L. Okay. So, when we want to obtain the relation, first we have to integrate the differential equation with respect to x. First we assume that dt per dx is equal to c1. So when we integrate this, we get c1x plus c2. Okay, c1 and c2 is just an arbitrary constant. Okay, so when we apply the boundary condition given, which is the x, okay, remember for the left side, which is inner surface, x equals to 0. So when x equals to 0, we use the formula negative k dt per dx equals to q. But dt per dx we replace by c1. Okay, so we make the c1 as the subject. So c1 equals to negative q over k. Okay, when the boundary condition is x equals to L, we use the general solution we got here, which is instead of x, we change to L. So TL equals to C1L plus C2. So here. And when x equals to L, the boundary condition is T2 also. So we equals to T2. Then we make the C2 as the subject. So C2, we move the C1L to the right side. So T2 minus C1 times L. Okay, then the C1 we replace by dt over dx. I'm sorry, C1 we change with negative q over k. Okay, so we already have C1 and C2. Next, when we already applied the boundary conditions, which is at the inner surface x equals to 0 and the outer surface x equals to L, we substitute the C1 and C2 that we got here into the general solution, which is this one. Tx equals to C1x plus C2. So for this C1, we substitute negative q over k. And for C2, we substitute T2 plus QL per k. Then after we substitute all that, we can get this equation. And if you can see, we have q over k here and q over k here. So we can factorize. When we factorize, we get q bracket this L minus with the x and divided by k, then we plus with T2. When we got this equation, we can substitute all the information that we have, which is we already got the q, and for L, it is already given in the question, and for x is unknown. K is already given to in the question, and T2 is already given in the question. So we got this. Okay, let's continue for C, part C. For part C, the question asks to evaluate the inner surface temperature, which is T1. So, T1. Okay, inner surface is this, on the left side. At this side, when if you want to find the temperature, based on x, it is equal to 0. So, just take this equation, then we put the boundary condition as x equals to 0, then this x will be 0, then we solve straight away this equation, and we will get T1 equals to 127 degrees Celsius. That's all.